Let's review chapters 4 and 6. As usual, go back to the original notes for more details, but we'll see the main ideas. So this first section, 4.1, studied division in detail, and we're working just with whole numbers, so no decimals or fractions needed. And just to see how it works, so if you divide, let's say, 82 by 7, doing it by hand, it looks like this. So 7 into 82, well, it fits in 11 times, but there's 5 left over. So 11 is the quotient, 5 is the remainder. So that's division. And the division algorithm is just saying the same thing. So these four numbers go together like this. We divided 82 by 7. It went in 11 times with 5 left over. So 82 is equal to the divisor, 7, times the quotient, plus the remainder. 77 plus 5, that looks good, 82. So A is equal to D times Q plus R. And that remainder, just the key thing about it, it's a number between 0 and D, so it has to be strictly less than the number you're dividing by. And 5 is less than 7. Okay, and we have this notation. So 7 divides 82 means that when you divide 82 by 7, you have a 0 remainder. It goes in evenly. So that's false here. We had a 5 remainder. So 7 divides 82 is false, or another way to say that, 7 does not divide 82. Okay, so just these remainders, that's an important idea in this chapter. Another way to think about it is in terms of a congruence. So A is congruent to B mod M. It means that M divides the difference. So this is also called an equivalence. And another way to think about it is that A and B have the same remainder when you divide by M. So an example here is 129 congruent to 111 mod 6. Okay, so these congruences, like equalities, they're either true or false. Well, the difference here is 18, and 6 does divide 18. Goes in 3 times with no remainder. So these two numbers are congruent mod 6, so this is true. Alright, so those are the main ideas we need, and the jargon and notation. Nice applications we looked at in the next section. So checking credit card numbers are valid. This is simple. That Lun algorithm just works mod 10. So you're just adding up the digits of the credit card number, doubling some of them, and that sum has to be 0 mod 10. If you do it and you get 7 mod 10, then it's not a valid credit card number. We also looked at pseudo-random numbers, another application. So this works using the linear congruential method. And so you have these fixed numbers. A is the multiplier, C is the increment, and M is the modulus. Okay, so you have these three fixed numbers. Then you can make a sequence of random looking numbers. So starting with the seed x sub 0. And it works recursively, so to find the next number, x sub 1, you put it into the formula. So you put in x sub 0 into the formula to get x sub 1. So multiply the seed by A, add on C, and then work that out mod M, so that's the remainder. And when you divide by M, it gives you x sub 1. And then repeat that, put x sub 1 in here to get x sub 2, put x sub 2 in here to get x sub 3, and you'll get this sequence. Yeah, it looks random. It's not really random. It's going to start repeating eventually, but good for applications and good for test questions too. Then we looked at numbers, factoring numbers in more detail. So any positive integer can be factored into its smallest possible pieces, its smallest possible integer factors. Those are the primes. For example, 56. Well, if you want to break up 56 into small factors, well, yeah, it's an even number, so you can break it up as 2 times 28. Yet circle 2, that's a prime, that doesn't have any smaller factors. But 28's not prime, it does factor, say, 7 times 4, and 4 is 2 times 2. So circle these bottom numbers. Those are the primes. You can ignore the middle numbers now. So the prime factorization of 56 is 2 times 2 times 2 times 7. You put them in order. You can also write that 2 cubed times 7. But this is the number 56 broken into its smallest possible factors. Yeah, that's called a prime factorization. Okay, so every number, well, 2 or higher, has a unique factorization into primes. You know, some numbers like 7, for example, what's the prime factorization of 7? Well, it's just 7. 7's a prime number. So if I give you a big number, how can you tell if it's prime or not? Well, we saw if a number does have factors, then one of them has to be less than or equal to the square root. You can't have all the factors bigger than the square root. Okay, so if you're checking to see if a number is prime, then just check the primes smaller than the square root. If none of these divide the number, then it has to be a prime number. Okay, so in this example, to show that 101 is prime, you just have to check divided by these numbers. If any of these divide 101, it's not prime, but if all of these don't divide 101, then it must be prime. So doing the division, yeah, if you divide 101 by 2, you get remainder 1, so 2 is not a factor. Dividing by 3, you get remainder 2. Yeah, 3 goes into 101 33 times, remainder 2. All right, not a factor. 5 is not a factor. 7, yeah, 7 goes into 10 once. 3 left over. 7 into 31 goes 4 times. Yeah, remainder 3. So 7 is not a factor of 101. Yeah, so that shows that 101 has to be a prime. And yeah, we don't need to check the next number 11. If 11 was a factor, then they'd have to be a smaller factor as well. Also, greatest common divisors. So if you look at two numbers, you can see what's the biggest number that divides both of them. And the best way to get the GCD of two numbers is the Euclidean algorithm. So this is the efficient way. And it works by repeating the division algorithm until you get a zero remainder. Example 3, find the greatest common divisor of 208 and 143. Okay, so yeah, usually we want the first number to be bigger than or equal to the second number. So 208 divided by 143, the quotient is 1. The remainder is 65. All right, now repeat that with these two numbers. So 143 divided by 65 next. Quotient is 2, remainder is 13. And repeat. 65 divided by 13. Quotient is 5, and now the remainder is 0. So that's what we're looking for. So when you get to a 0 remainder, you can stop the algorithm. And the answer is, yeah, it's not 0. The answer is the last non-zero remainder, 13. So the GCD we were looking for, the biggest number that divides both of these is 13. All right, yeah, so these are fairly big numbers, so this works. You can see how efficient it is. And yeah, just to double check, so yeah, if you break up 208, it has these factors: 2 times 2 times 2 times 2 times 13. 143 is, yeah, you could start dividing by primes. Yeah, you have to get to 11. It's 11 times 13. And yeah, so the only factor they have in common, the greatest and only factor is 13. So the Euclidean algorithm checks out. In this case, 13 is definitely right. Okay, so yeah, you'll probably be asked to do one of those on the test. Also a nice question, converting between bases. So we're used to working base 10, but if you have a base b representation of an integer, we write it like this, parentheses with a little b here. So this means that instead of tens, we're using powers of b, so each digit is multiplied by a power of the base b. The first digit, d sub 0 here, that's always times 1. The next digit is times b to the power 1. This guy times b to the power 2. Okay, so each next digit is multiplied by a higher power of b. But yeah, don't forget, the first guy it's like b to the 0. It's always the units, the ones, for this right-hand digit. Okay, so 562 base 7. Let's convert that back to base 10. So this means 2 ones plus 6 sevens plus 5 7 squareds. Work that out, that's 289. Alright, so this is the base 10 representation, but yeah, we just no need to write this for base 10, it's just the regular number. How about ABC base 16? And yeah, so if your base is bigger than 10, you need extra digits. So A means 10, B is 11, 12, so we need the digits up to 15. Yeah, if you're working in base B, the digits represent numbers 0 through b minus 1. Alright, so this is the hexadecimal system, base 16, but it's the same as base 7, the same idea, so it's C1s, B16s, A16 squareds, where C is 12, B is 11, and A is 10. Alright, so the hexadecimal ABC, that's in regular numbers 2,784. Alright, so that's converting from a base back to base 10. In the other direction, if you're converting a base 10 number to a different base, then you just keep dividing by the base. Alright, so if we want 289, convert that to base 7. Well, 289 divided by 7, we get a quotient of 41 and remainder 2. And now take that quotient, divided by 7, divided by the base again. Quotient 5, remainder 6. And then 5 divided by 7, quotient 0, remainder 5. So stop when you get a 0 quotient. And then it's these remainders that we need for the digits. And we need them in reverse order, so this 5 is going to come first. So 289 is 562 in base 7. Yeah, so we've just gone backwards. Yeah, we're back to 562, base 7. Yeah, we didn't need any A's, B's, C's, D's, E's, F's here because the base was just 7. We only need numbers 0 through 6. But if we were getting any remainders like 15, we'd have to convert that to an F. Okay, so just using this, these extra digits we need for bigger bases. Yeah, just the capital letters. Alright, so that's chapter 4, looking at numbers, primes, GCDs, different bases. Chapter 6 is different ideas. So ideas of counting, especially counting the number of ways things can happen, or the number of ways some choices can be made. So we're getting into permutations and combinations of things. And the main first idea, so if you're trying to count something complicated like this, you have to break it into steps or tasks. For example, how many ways can you order a Chinese meal? If there are 30 meal options, 30 meal choices, each with white or brown rice and 5 possible sodas. All right. So you're looking at the menu. Well, we can break it into tasks. So first we'll choose the meal. So that's the first task. There are 30 ways to do that. Okay, that's the hard part. Task 2, choose the rice type, so two options there, and then the soda. That's the third step, the third task. There are 5 ways. And what do we do with these numbers? Yeah, so in this situation, with these separate tasks, you multiply the numbers to get the total number of ways, the total number of choices. So that's 300. Okay, so in this situation there are 300 ways, 300 different meals you could get. And yeah, so if you label the meals M1, M2 to M30, the types of rice R1, R2, the sodas S1 through 5. Yeah, so you could list all these possibilities. It's going to be a long list, 300 things in the list. Okay, so that's the product rule. If there are X ways to do the first task and Y ways to do the second task, then you have X, Y ways to do both tasks, and keep multiplying for more tasks. Okay, just to see a slightly different situation, suppose you're only going to order one item from the 30 meals, 2 types of rice, and 5 sodas. How many ways to do this? Okay, so now you're only ordering one thing instead of 3 things. And you can see, if you're only ordering one thing, then you just have 37 possibilities, so you're summing. Okay, so the difference is, if you just have one task, with say X options or Y options or Z options, then there are just X plus Y plus Z ways to do that one task. or make that one choice. Alright, so I hope you see the difference. So yes, so sometimes you're adding, sometimes you're multiplying, sometimes you're subtracting as well. So if a task can be done in X ways or Y ways, and Z of those ways are the same, then there are really X plus Y minus Z ways to do the task. Alright, so that's a subtraction rule. Let's see an example. Example 6, in a group of 50 people, suppose 30 have been to Maine and 25 have been to Alaska. Okay, 30 and 25, that's more than 50, so yeah, there must be some overlap. If 10 people have been to both states, how many have been to Maine or Alaska? Alright, so you're back. Remember our logic, so or is really inclusive. It means Maine or Alaska or both. Alright, so what's the task here? Well, yeah, we're trying to choose people who have been to Maine or Alaska or both. Well, yeah, we see 30 people have been to Maine, plus 25 people have been to Alaska. But some of these people could be the same, so we have to subtract the same people, so that's 10. Okay, yeah, so these 10 in the overlap, yeah, they get counted twice if you just do 30 plus 25, so subtract 10 to get them once, so that's 45. Alright, so that's the answer to the question. 45 people have been to Maine or Alaska. Yeah, there were 50 people in the group, so that means 5 haven't been to either state. Yeah, I don't think I've been to Maine or Alaska. Okay, yeah, we also saw a nice way to picture this is using Venn diagrams. Okay, so the rectangle has 50 people, but that breaks into 10 in each section. There'll be 20 people who went to Maine and didn't go to Alaska, 15 people that went to Alaska and didn't go to Maine. Okay, so yeah, so draw a Venn diagram. Okay, so an application of the product rule is to permutations. So suppose you have n things, then the number of ways to arrange r of them, that's called a permutation number, p n comma r. Okay, so out of the n things, you're picking r of them, so it's r tasks, n ways to pick the first, then there are n minus 1 things left, so n minus 1 ways to pick the second, n minus 2 ways to pick the third, down to n minus r plus 1 ways to pick the rth thing. Yeah, so there's a plus 1 here. It's a bit confusing, but yeah, we're really multiplying r numbers together, so that's a good way to keep track. Okay, so start with n and go down, multiply these r numbers together, that's the permutation number. For example, a festival is choosing 4 bands out of 10 available bands for a concert. How many possible lineups can the concert have? Okay, so for the lineup, yeah, the order is important. So who goes first, second, third, and fourth? So this is a permutation number we need. So it's 10 times 9 times 8 times 7. So these 4 numbers, starting with 10. So there are 5,040 possible lineups. All right, so that's permutations. Now the other situation, you have n things, you want to choose r of them, but you don't care about the order. Then that's called a combination number, c n comma r, or n choose r. So it's the same permutation number on top, but then you just divide by the number of ways to permute those r things. Okay, so this combination number is going to be smaller. You just divide by the number of ways to mix up those r things. So that's r times r minus 1 down to 1. Okay, so yeah, really p r comma r on the bottom. All right, so that's a combination. So yes, it's r numbers on the top, r numbers on the bottom. The top numbers start with n, the bottom numbers start with r, going down to 1. Okay, so slightly more complicated. Example 8. Suppose 10 people are at a restaurant, and 4 of them order dessert after the meal. How many ways can this happen? In other words, how many ways can you choose 4 people out of 10 people? Yeah, we don't care about the order in this question yet. The order is not important, so we need combinations. See 10 comma 4, yeah, so it's 10 times 9 times 8 times 7 over 4 times 3 times 2 times 1. Yeah, so you could multiply out these numbers, but much better to cancel. So yeah, we really have an 8 on the bottom, 4 times 2, and cancel the 3 out of the 9. Okay, so that's what I'm doing here. So it's, yeah, we're left with 1 on the bottom and 10 times 3 times 7 on top, so 210. Yeah, so for these combinations, you work them out by canceling. All right, so there are 210 ways that 4 of the 10 people can order dessert. All right, so yeah, when you're looking at combinations, yeah, it's always smaller than the, yeah, here we're choosing 4 from 10, but we care about the order, so there are lots more ways. Permutations give bigger numbers. All right, in this last section, binomial coefficients, so looking at these n choose r numbers in more detail. Well, an application and also different notation. So another way to write them is like this, just with parentheses, n on the top, r on the bottom. Okay, so they're called binomial coefficients because they show up in the coefficients when you're looking at powers of binomials. Okay, so we have this binomial theorem, which just gives a formula for powers like this. So if you have a fourth power, then you just have a 4 on top. Okay, and you need, so for x and y, you need powers of x and powers of y. The sum of those powers has to add to 4, and one of them should have a matching power. And so 4 choose 0, x to the 4 times y to the 0. 4 choose 1, x to the 3, y to the 1. Okay, so we get this pattern all the way over to 4 choose 4, x to the 0, y to the 4. So working these out, yeah, it's so multiplying this out, you get this formula. And these binomial coefficients, yeah, 1, 4, 6, 4, 1. So that's the pattern, that's the binomial theorem. Yeah, that's the basic formula. More complicated versions have, say, the x replaced by something, the y replaced by something. So then this will get more complicated. For example, replacing the x by 2x and the y by a number, -1. So now we're working out the fourth power of 2x minus 1. Okay, so now all these x's get replaced by 2x, and all the y's get replaced by -1s. Use parentheses. So we get this, and then working this out, it simplifies to this. Yes, that last term, for example, yeah, 1 times -1 to the power of 4. Well, -1 to the power of 4 is 1, so that turns into just a 1. Alright, yeah, so this binomial theorem, yeah, we're just looking at the 4 case, but yeah, it's very, very useful. And yeah, in this section we also looked at Pascal's identity and Pascal's triangle, so making a triangle out of these coefficients. Alright, so that's just a quick review of chapters 4 and 6.